Okay, so today I thought we could discuss a little bit of maybe some Markov chain stuff and Markov chain Monte Carlo. Again, this being a survey course, we're just going to kind of scratch the surface of this topic, and like so many of the other topics we've covered, you can take an entire course devoted to this. So I'm trying to figure out what I can fit in the next 2.5 3 hours of content. So let me just talk about why we want to even bother with Markov chain Monte Carlo stuff, and in particular, we will look at like the Metropolis Hastings algorithm and the Gibbs sampler. So, well, the Metropolis algorithm, and it's very much related, Metropolis Hastings. And, the Gibbs sampler, and in all of this, again, the topic being MCMC, being Markov chain Monte Carlo methods. And let's talk some. First of all, we'll talk about what the applications are and how it fits in. So these algorithms, the Metropolis algorithm, the Gibbs sampler, the primary application is basically density estimation. We are trying to figure out the density of some probability function, but this probability function is just too hard for us to get the density directly. Okay, so this is kind of the biggest application is estimating a probability density where it is too hard to figure out the density directly. Okay, and so we looked at Bayesian statistics last week, and this is a lot of times in Bayesian statistics, we turn to these MCMC algorithms in order for us to get the posterior distribution. So, big application is in Bayesian statistics. So, for example, we would say, we want to get the density of some set of parameters. I forgot what letters I used, but maybe we'll say we have some parameter vector theta based on, the data that we have, x, and some other stuff. Okay, and in Bayesian statistics, this is basically the likelihood times the prior divided by the marginal, which would be the probability of getting our data given the parameters theta multiplied by the prior distribution theta divided by the marginal distribution x, okay? And, you know, last week our example was the beta binomial with the coin, and we said, you know, this was a nice one because the beta distribution is a conjugate prior, which basically just means we have an analytic solution to this thing. We have, if we use the beta distribution for the prior distribution, it combines nicely with our likelihood, and so it ends up in the same form. You know, sometimes we have nice analytic solutions, okay? Okay, but many times we do not, okay? And so, and especially getting this thing, getting this normalizing constant is often very difficult. Okay, and so how can we figure out what this distribution looks like, right? So what does this look like? Okay, what is its mean? What's its standard deviation? What's its shape? These are all questions we want to know, right? Okay, and it might not be clear, especially if we're not using conjugate priors, if we're not using these things and that have these nice little properties. So what MCMC allows us to do is it allows us to kind of get an estimate of what this thing looks like. And the beauty of it is we don't have to figure out this normalizing constant. We can just say, okay, our probability of our parameters is proportional to this. So we know the distribution up to some normalizing constant. Sorry, something just happened there. So we know it up to some normalizing constant. Okay, and we can generate a sample using one of these methods. Okay, so we can generate a sample with MCMC. Okay, so that's one application. We'll see if we have time for another application, but this is probably maybe one of the most important applications of these MCMC methods. In Bayesian statistics, we'll often have a distribution that says, you know, we think our answers can be found in this distribution. The problem is I don't know what this distribution looks like, okay? Because, you know, we can multiply this out. You know, the likelihood is, you know, you set up your model and you say, okay, well, this is going to be the probability of my data, and you say, okay, well, this is the distribution I have on the parameters prior to looking at the data, but then we just don't know what that looks like. Okay, so how does this work? Okay. Okay, so let's, I guess we'll back up and we'll talk about what a Markov chain is, and we'll talk about Monte Carlo, and we'll build maybe one of these algorithms up. Okay, so a Markov chain basically you have it's like a series of states, and so the Markov chain, we have a series of quote states, and or like what kind of status our thing is in, and we can transition from one state to another. Transition, or in other words, change. From one state into another. And the Markov property is that the probability of changing to the next state, whatever that might be, depends only on the current state. Probability of what state I transition to depends only on the current state. Okay, so the past history before my current state does not matter. Okay, and this this Markov property may not be 100% accurate, but it can serve as a decent approximation of reality. Okay, so so sometimes you'll see like sentences. So when you on your phone, if you have like a keyboard that predicts what words you will type next, they're using some form of a Markov chain, but probably not exactly with this single state dependence Markov property. Okay, so if you say if you type in I, then the next, what word will come next if your current word is I, you probably have high probabilities for am, high probabilities for will or something, and then low probabilities for is or be, and then, a bunch of other words will have low probabilities, right? Unless we're trying to be ironic in our speech, but words like am will have a higher probability, and so as soon as you type in I and then hit and you hit space, then your keyboard will show up 3 choices of words you can do, and I imagine am would be one of those predicted things. Okay, and then if you say like I am going, okay, then there's going to be a very high probability for the word to, or something like that. And with the Markov property, basically we're just saying the next word only depends on the current word. Okay, and in English we know that there's certain phrases and certain sequences of words that are much more likely than others. Okay, that's kind of what we have. It could be applied onto a so if you have the word I, then next word high probability for am or will, etc. Okay, low probability for is, be, I don't know. Okay, but it could also be applied to words on a letter by letter basis. So this is kind of like for words, but for letters, you could have like if you have the letter Q, then you got very high probability for U, right? And low probability for almost every other letter for what comes after Q. And then other things like if you have the letter I don't know, the letter E, then almost like many other letters will have a high probability, and I don't know exactly what's going to come next. Okay, now in English, it's not with Markov properties, we can only look at one letter at a time, whereas in reality, if you see the letter I and followed by the letter N, then there's a very high probability of the letter G, right? So much so that sometimes when you're typing things and you have IN, sometimes you accidentally hit G out of like muscle memory, even though that's not really the next letter. We would not be able to model this with the Markov property because because this has two states, right? So this is not not necessarily your strict Markov property. But you can, a lot of models and your keyboard prediction things probably allows for more than one. So it's not a strict Markov chain thing, but a modified one. Okay, so let's just try a simple, you have the thing with Markov chains is there's something called a stationary distribution. So for a Markov chain, you will have a transition matrix. The transition matrix represents the probability of going from one state to another state, okay? And then the Markov chain has what's called a stationary distribution. The stationary distribution is if you allow the Markov chain to run, it will converge to a stationary distribution, okay? So if we allow the Markov chain to run forever, converge to the stationary distribution, okay? And the stationary distribution is where each state, the probability of the state remains the same from one to the next. That the amount going into this state and the amount leaving the state is at equilibrium. Okay, so when when the chain, I'll illustrate with an example. I think it will make more sense, okay? When the chain converges to the stationary distribution, that means that every state is in equilibrium. So the amount coming into the state, the amount transitioning to that state equals the amount transitioning away from the state. Okay. In order for the Markov chain for us to say it's going to converge to this stationary distribution, it does need to meet certain criteria, meaning it has to be, ergodic and aperiodic, which basically means that each state can travel to every other state at some point. Maybe not a direct flight, but basically that no state is impossible to reach. Okay, so So I'll just write this. This is kind of like an asterisk. Chains must be ergodic and aperiodic. Ergodic or ergodic. I don't know how to pronounce these things. Ergodic means you can reach any state from any state. So if you start at one state, you can reach any of the other states, okay? Given enough time, maybe not directly, maybe you have to, like if you're in Los Angeles and you want to get to New York, maybe you have to travel through Albuquerque and St. Louis or something. Like maybe you have to there's no direct path to there, but if you can reach there, great, okay? And then aperiodic, so formal math, there's more complicated things to say. But at a practical level, aperiodic just means at least one of the states you're allowed to stay in that state for the next turn. Like if you don't want to transition to another state and you just want to stay put, at least one of the states has this property where you can just stay put, okay? So at least one state allows you to stay put. All right, so here's just a bunch of terminology up on the screen right now. What do these states even mean? Okay, let's just try out. Okay, so let's say we'll keep it real simple. We'll say two states, A and B. Okay. Okay, and we will say from A, you can either transition to B, or if you wanted to, you can stay put in A, and that's going to be represented by the arrow going back to A, all right? So if you're at A, you can go to B, or you can remain in A, okay? This would not be ergodic or irreducible or whatever, meaning that if you're at B, you can't get to A. But as soon as I draw this thing, then we're good, okay? And we'll do this. So if you're at B, you can also go to A. You can also stay at A. Okay, and let's say if you're at A, we'll say there's 30% chance of going to B, which means there's a 70% chance you remain in A. And if you're at B, we'll say there's a 40% chance of going to A, meaning there's a 60% chance you remain in B. Okay, so our transition matrix would be would look something like this. So we'll say now, and this will be next. This is A and this is B, okay? And so if you're now at A, then there's the probability you end up in A next, it'll be 0.7. If you're now at A, then the probability you end up at B is going to be 0.3. If you're now at B, the probability you end up at A is going to be 0.4, and from B to B is going to be 0.6. Okay, this is our transition matrix. Okay, and so what is the stationary distribution? The stationary distribution is basically the, quote, population of A, or proportion population, or we can just say proportion of A and B, proportions or populations of A and B, so that the amount leaving is the amount same as the amount coming in. All right, so let's just what is that? So basically it has to be, so if we have A going to B, 0.3 of A goes to B, that has to be equal to the 0.4 of B that's going to A. So if we look at this part, okay, and so and then the other, and then if we're looking at proportions, A and B have to equal 1. So I'm going to have 0.3A equals to 0.4 times 1 minus A, and then I'll have 0.3A equal to 0.4 minus 0.4A. And what do I have? 0.7A equals to 0.4. I don't know what 0.4 divided by 0.7 is. Okay, 0.5714. Okay, so A will equal 0.5714, and B will be 0.4286. Okay, so basically 4/7 and 3/7. So so if we'll call this pi. Pi is often what we call our stationary distribution. The stationary distribution of A and B will be basically 4/7 and 3/7. Okay, and so if I have 4/7 here, and if I have 3/7, we can see 4 times 0.3, this would equal what is this, 4/7 times, I don't know, 1.2, 12/70ths. Okay, this will be 12/70. And then same thing over here, we will have 12/70 going this way. So if you think of this as, if A just has a population of 4 million and B has a population of 3 million, okay, then at every iteration, at every step, you know, about 30% of 4 million, so 1.2 million, would go from A to B. And then if B has a population of 3 million and 40% of that 3 million goes, then 1.2 million goes to A. So at that point, the amount going from A to B is equal to the amount going from B to A. And so here we have reached a point of equilibrium here. Is that okay? What's happening there? All right. And so, you know, we can model, I don't know, some population things, right? Like how many people move from California to Texas each year and how many people move from Texas to California each year. You know, we can look at that and then, you know, but the vast majority of Californians probably stay in California the following year, and the vast majority of Texans probably stay in Texas the following year. But, you know, we can kind of look at the amount that transitions from one place to another and reach a point of equilibrium. Okay. An interesting thing about this is that once you set up, if you have your transition matrix, the stationary distribution will be one of the eigenvectors of that transition matrix. Okay, so the will equal one of the eigenvectors of the transition matrix. So so this is kind of the beginnings of just what a Markov chain is. You just you start somewhere, and if we were to draw samples from this Markov chain, it might look something like this. We might start at A, and then we'll flip a coin, or you know, we draw a random number, and then we say, okay, oh, we ended up at A again, and then given at A, you know, maybe we end up at A again, and then at some point we transition to B, and then and maybe we stay at B, maybe we switch back to A, and who knows what would happen. Okay, you can end up staying in one of these states, so on and so forth, et cetera, et cetera, et cetera. And it's just that after drawing many random samples, basically at each turn, you're just going to pick a random number. If it's less than 0.7, you stay at A, and if it's greater than 0.7, between 7 and 1, you transition to B, and you do the same thing at B. If it's less than 0.6, you stay at B, and if it's greater than 0.6, you transition. And then after many, many, many iterations of transitioning, you can get an approximation of the stationary distribution as well. Okay, and that's just one chain there. Okay, so we can expand on this idea of a Markov chain to be something a little bit more useful for us. And so we'll look at the metropolis algorithm. So the okay, so the Metropolis algorithm, this is going to be an application of basically a Markov chain. And the idea is we continue to just follow the rules and draw you know, random states following the rules of the Markov chain. Okay, we follow the rules and draw random states from the chain. And after enough iterations, you know, what, you know, the values we've drawn will resemble the stationary distribution. Okay, I just want to pause here and make sure everyone's okay with what I've talked about so far. Just conceptually, the idea of a Markov chain having a transition matrix representing how likely we are to go from one state to another. The idea of drawing random samples using that transition matrix that eventually takes us to a stationary distribution, or something that resembles the stationary distribution.
So are we then, like using the example from before with A's and B's, are we just drawing I don't know.
Yeah, here, maybe I can just code something up very quickly to kind of show this how we might do something like this, right? Okay, so we'll just we'll write our current state.
Shifting the screen a little bit.
Oh yeah. Okay, so we'll just say our current state is A. Okay, and then we will we'll run a loop. Okay, so we'll just say for I in 1 through 10,000 or something. Okay, and we'll just say if state is equal to A, then what we're gonna do is we'll draw a random number. Our UNIF is a random number, and if this random number is less than 0.7, then our state will remain A. Okay, and I need to put this in a else. If it's that, we'll do that, and otherwise the state will transition to B. Is that okay? All right, and on the other hand, else, meaning the state has to be B, then we will do the same thing. We will draw a random number, but this time if it's less than 0.6, we will keep our state to be B, and otherwise if it's greater than 0.6, we will transition to state A. Is that okay? And then to kind of keep track of this, I'll create a results vector, which will just be $10,000, and we'll do results I will be whatever state we have. Okay, does that code make sense for what's happening? We're looking at our state, we're going to flip a random coin, or draw a random number. If it's less than 0.7, we stay put. If it's not, we're going to transition to state B. Okay, and then when we check the other ways, if the state is B, which must be the case with else here, and we'll do another thing. And if that's less than 0.6, we will stay at B. Otherwise, we will. Okay, I just wrote this on the fly, so I hope it works. There's always a risk that it doesn't. Okay, and then okay, so it's done. All right, and then let's see how many of our results is equal to A, and we're hoping for something around 4/7 out of 10,000. Let's see. What is 4 divided by 7? Okay, kind of close. Okay, not perfect. I guess if I did 100,000, we'd probably get something closer. Okay, it's done, and then let's just the mean. Yeah, that's pretty close, right? So here, we just ran it 100,000 times, and the results of all of these transitions, which is what it's doing, gives us something close to our stationary distribution, right? So if I just do results, we'll just look at the first 100. We can see B, 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 A, we're at A for a while, then we transition to B, then we transition back to A, then we go to B, and so on and so forth. And it's just sometimes at B you just keep flipping the coin and you stay at B for a long time, something like that. Okay. And then, if we change the rules and we say, all right, you know what, maybe there's a 95% chance if we're at state A, there's a 95% chance of staying at state A, and we'll still say there's a 60% chance of going from B to A, right? So the stationary distribution here is going to be much different, where we're going to end up at A a lot more. And what did I say? Mean of results equal to A. Okay, and then now we get a, something around 89%, and I don't know, is that right? 5 plus 6. Yeah, I don't know, something. Okay. Anyway, this is what we have here. Maybe let's say 0.05 plus 0. Okay, so I think theoretically the stationary distribution is 8/9 versus 1/9 or something. If I have so it's pretty close, 0.888 versus 0.89026 or something like that. Okay, so anyway, that's this is just a very simple case for a two-state Markov chain. Here, I'll put this code up on two-state Markov chain. Transition probabilities will be if at A 2A is equal to 0.7 and to B would be equal to 0.3, and then if at B 2A would be 0.4 and to B would be 0.6. Okay, so I'll save this to chain 1 chain.r. I'll upload this here. Oops. This is the wrong button. Okay. I gotta log in here. Okay, so we have so that's a simple Markov chain with just two states, right? Here we'll do the Metropolis algorithm, and the Metropolis algorithm gives us kind of instructions for creating a transition matrix over several states that, if we set up our transition matrix, following these rules, then our stationary distribution will look like the target distribution that we are hoping for. Okay, so let me write this down, and then we'll do an illustration to explain this. Okay, so the Metropolis algorithm is an application of a Markov chain. We follow the rules and draw random states from the chain. After enough iterations, the values we have drawn will resemble the stationary distribution, and the Metropolis algorithm basically gives us rules regarding our transitions so that the target distribution, or so that the stationary distribution of the chain, distribution of the Markov chain, will equal the desired target distribution. Okay, and what it requires is that we are able to calculate kind of the density up to a proportionality constant of the target distribution. Okay, so the only thing that is required is that we can calculate P of x, the PDF of the target distribution, or at least something proportional to that target distribution. Proportional to it. Okay, which is great because, like I said, back in for Bayesian statistics, oftentimes we have a target distribution that we want to get a hold of, but it's so complicated, we don't know that normalizing constant, and so we can at least get something that's proportional to it, even if we don't know the value that goes in the denominator, right? So, because so if we want probability of theta given x, and we say this is times this divided by this, we can eliminate this and just use the numerator because we have something proportional to our target distribution, right? So this is great. Okay, so how does this work? Well, we'll start with we'll do an example to kind of explain how this will work. Okay, so let's say example to illustrate. Metropolis algorithm. All right, so let's say I don't know, there's like some island nation, all right, and island nation is we have, it's a chain of islands. Okay, and and we'll say, somebody, we'll say a politician. The reason why we're picking a politician is because the politician is going to try to visit all of the islands. With a frequency proportional to the population of the island. Okay, islands with a frequency proportional to the population of the island. Okay, so in our example, Island 7 will have the greatest population, and Island 1 will have the smallest population, just for simplicity. And so in this case, the politician wants to make the most number of visits, campaign visits, to the island with the greatest population, and fewer visits for the island with smaller population, so that the whatever, because he's campaigning. All right. The problem is that we do not know the exact distribution of the population of all the islands. Okay. Okay, what we are able to get the current island's population, whatever island we are currently on, and the population of the neighboring islands. Population of the two, or of the immediately neighboring islands. Okay. Of course, this is a contrived example, because if you're able to get the population of the neighboring islands, it's just a matter of bookkeeping to get the population of all the islands. But just in this example, we'll pretend we can't get the whole distribution. We can only get like immediate things, okay? And as far as the travel goes, the politician each day has an option, either to stay on the current island, go to the island to the right, or something with a higher number, or going to the island to the left, or the population or the island with a smaller number. Okay, and make another, quote, campaign stop or visit the following day. Okay, so each day the politician can stay on current island, go right, or go left. Okay. Is that okay? So, so what we will do, so this is going to be the metropolis algorithm. for our island case. Okay, for the islands. So at each day, we will flip a coin to decide to go left or right, okay? And then what we'll do is we will find our current population. Okay, actually, I shouldn't say decide. It should be flip a coin to propose going left or right. So not decide, but because the decision comes at the end. To propose. Okay, so we flip a coin to propose to go to the left or to go to the right. Okay, we will find our current population, and then we will find the population of the proposed island. Okay, now if you are at like the end island, so that's like island 7, and you flip the coin and it says go right, meaning it proposes quote island 8, but island 8 doesn't exist, then you would have the population of the proposed island would be 0 because that island doesn't exist. Okay, or same thing with if you're at island 1 and you flip the coin and it proposes going to the left, that's gonna have a population of 0. Okay, so if the coin flip proposes a non-possible state or non-possible island, then that quote island has a population of 0. Okay, so we find the population of the proposed island, and then we will decide whether to stay put or to move to the proposed island based on the following rule. Decide to stay put, meaning spend another day on current island. Or move to proposed island based on the rule, okay, which is if the proposed population is greater than the current population, definitely go. Okay. If the proposed population is less than the current population, then excuse me, thank you. Then there's still a chance of going. If the proposed population is less than current population, then basically draw a random number from 0 to 1, okay, using basically like RUnif, and we will say go with probability, we will call this P move, equal to the proposed population divided by current population. All right, so if the proposed population has a population 70% of your current population, you will transition there with probability 70%. And you will remain at the current island with a probability of 30%. Okay, so does that kind of, at least, like if you were given these instructions, you could follow these instructions. Okay, well, so I'm not going to try to prove that this works, but if we follow these rules, then what happens is the Markov chain, all of the islands that we visit, we will visit relative to their actual populations. Okay. Okay. So here, let me just write this. Draw our unif 1, and if our unif is less than p move islands. Okay, so let's yes, question, guy.
So the first thing I thought of is that what if one of the islands is farthest away from the start point has a very high population? Would that end up being underrepresented?
No. This is the amazing thing about the Metropolis algorithm is that you will end up there. So here, let me back up before. Wow, no, I don't know if I need to back up, but so when you set up your transition matrix, I said the stationary distribution is an eigenvector of your transition matrix. Okay, so the eigenvector, what is an eigenvector? So if you keep multiplying the transition matrix to itself, okay, eventually it will converge. Like if you start off with any data point, any location, and you multiply it by the transition matrix, or you multiply any point on the plane and you multiply it by a square matrix, and you keep multiplying by that square matrix, eventually, so the matrix applies basically a transformation to that original starting vector. And if you do it often enough, it's going to all converge to a location along the eigenvectors of that transition matrix. There's actually a beautiful, give me a thing. There's a beautiful illustration on this on a website. I think it's called Explained Visually. Eigenvectors. Let's try Markov chains. Okay, so with an oh, look at this. So if you keep multiplying some vector v by a, I don't know if you guys can see this, then the eigenspace attracts that sequence, and the eigenvalues tell you. So as we continue to multiply v by the matrix A, it gets closer and closer to something on the eigenspace here. Let me just see. So here, Okay, so here we have amoebas in a petri dish. Every minute, all amoebas produce one child amoeba, and all child amoebas grow into adults. Okay, this is what we're going to do. So if t is a minute, the equation of the system is adults is going to be equal to the number of adults plus children, and the number of children will equal the number of adults. Okay, so we're going to start off with one child, and when I transition, then it becomes one adult. And then at the next step, we're going to have the adult produces a child. And so we got one child, one adult. And we'll go forward. Okay. The child grows up into an adult, and the adult produces another child. Okay. So here I've got two adults and one child. So at the next state, this child will grow up into an adult, and the two adults will produce two children, right? So we've got two children and now three adults, okay? And now we have 1, 2, 3, 4, 5 adults and 3 children. And then so at the next step, we will have, what, 8 adults and 5 children, right? Okay, and what we see, this gray line represents the eigenvector of this transition matrix, which is 1, 1, 1, 0. Okay, so here kind of represents what's going to happen at the next thing, and we can see as it continues, we get closer and closer to right along that that eigenvector. Okay, same thing here. We start off with some population, and so this is I guess 90% of Californians stay in California, and then 70% of New Yorkers stay. And so here it shows where it transitions, and you can see over here where the next state ends up being. This arrow represents the eigenvector of this transition matrix, and we will see that after each iteration, no matter where I started, we get closer and closer to this eigenvector, which represents the steady state. And so, but anyway, yeah, let's to illustrate this, and we can see we're right on that eigenvector there. Okay, what's this over here? Yeah, this is okay. We don't need that one. So yeah, even if we have a high population at one of the end zones or whatever, we will visit that. Given that the chain runs long enough, we will visit it with the appropriate amount of times. Okay, so let's just say, just to kind of illustrate how this works, let's say we've got our 7 islands. Okay, and let's just say, so we've got islands 1 through 7, and just for simplicity, we will say the population of island 1 is 1 million. Oops. And the population of island 2 is 2 million, and population of 3 is going to be 3 million, and then so here is basically 7 million, all right? So each island, their population is exactly that number, okay? And so let's talk about, let's build a transition matrix, okay? So I'm going to have from to 2, okay? So we've got state 1, 2, 3, 4, 5, 6, 7. We can start at any of these states. And we can talk about the probability of transitioning from one to the next, okay? So let's say I start on island 1. Okay, I've got a population 1 million. Island 2 has a population of 2 million. So what are the rules? We're going to wake up. We're going to flip a coin to propose going to the left or going to the right. So I've got a 50% probability of proposing to the left I got a 50% probability of proposing to the right, okay? If I propose to the left, what happens? I would say, I look to the left and I say there's no island there. So if I propose to the left, then that means I'm going to stay put for the day, right? So the probability of staying put is going to be 0.5. And if I propose to the right, what was my rule for moving? I check, I call up, and I say, what's the population of the island I've proposed? And if it's bigger than my current island, I'm definitely going to go, all right? Island 2 definitely has a population 2 million, which is bigger than my current island. So I'm definitely going to go to island 2. So if I start off island 1, the next day I could either end up at island 1 with probability of 0.5, I can end up at island 2 with probability of 0.5, and I've got no probabilities of ending up at any of the other islands. Is that okay for our first transition matrix? Okay. All right, let's say I start at island 2. Okay. At island 2, I'm going to wake up, I'm going to flip a coin, and I'm going to propose either moving to the left or moving to the right. Let's say I propose moving to the right. What's the probability I'm going to end up at island 3? That's going to be 0.5, right? Because if I flip the coin, it says go to the island 3, I'm definitely going to go to island 3. Okay, if I propose going to island 1, then I say, well, I might go to island 1, I might stay put, okay? What's the probability I would go to island 1? So the probability of moving from island 2 to island 1 is going to be equal to the population of island 1 divided by the population of island 2, which is going to be 1/2. Okay, so the probability of going to island 1 is going to be 0.5 times 0.5, so I have a probability of 0.25, and then that means this will be probability 0.25. Okay, and then everywhere else, I got a probability of 0. Okay, let's do island 3, okay? If I'm at island 3, I could propose island 4, and I will definitely go there with probability 0.5. Okay, and I definitely can't go to island 1 or 5 or 6 or 7, okay? And then so we will say, all right, what's the probability of moving from island 3 to island 2? That's going to be 2/3, right? So that's, if I've proposed island 2, then I will move to island 2 with probability 2/3. So then the total probability of moving to island 2 would be 2/3 times 1/2, which will be 1/3, okay? So I'm going to just write 1/3, which means the probability that I stay put is going to be 1/6. Is this okay with everybody? All right, and then island 4, we can go to island 5. If I propose island 5, I'm going to propose it with probability 0.5, and if I do, I would definitely go there. I can't go to island 1 or island 2. I could propose island 3 with probability 0.5, and I would actually go to island 3 with probability of 3/4. So 3/4 times 1/2 would be 3/8, and I would stay put with probability 1/8. Okay. All right. So what does this one look like? So 5 to 6 has probability 0.5. What's the probability of going 5 to 4? 0.4 and 0.1, right? Or is it okay? And then, okay, let's do, so I can go from 6 to 7 with probability 0.5. 5/6, so I would, if I propose, I would go 5/6, so this has a probability of 5/12, and this will be 1/12. Okay, and then the last one is a little bit tricky, okay? So I could propose going to island 8 with probability 0.5, which means I would stay put with probability 0.5. If I propose island 6, I would go with probability 6 out of 7. And so this would be 6 out of 14. And I would have 1 out of 14 in remaining on island 7. But I have to add that to the 0.5 remaining, so I would have 8 out of 14 here. Okay, so this is, I don't know why this is not centered, but so this is my transition matrix. Okay, and basically every single island also looks like this. So the entire thing, this is our full arrow diagram. We can go from every island, we can either go to the one to the right or one to the left, or we can end up at the self, okay? And so this is because from any island we can reach any other island, and at least one of the states has a thing where you can go back to itself. This is ergodic and aperiodic, and so the thing holds up. Okay. All right, so I have, this is my transition matrix, and I guess I'll, do I want to do this? Well, if we set this up and we calculate the eigenvectors of this transition matrix, we would get our we would get an eigenvector that is proportional to this thing. Maybe I'll. Oh, it's already 7:30. Okay, why don't we take a break, and then during the break time I'll code this up here, so you don't have to sit and watch me type this. Okay.